Welcome back for another episode of VMC Chemistry. Right now we're going to do Charles' Law. It's still part of Unit 2.4, so it's another simple gas law, one that you observed at the lab when you did that super duper lab 2 weeks ago. So this one is about volume versus temperature. First point I want to make is that all your temperatures, when we deal with simple gas laws or gas laws in general, have to be in degree Kelvin. So to convert degree Celsius into degree Kelvin, you now know that we need to add 273 to our temperature in Celsius in order to get the equivalent in degree Kelvin. If we want to go back, obviously we're going to take our temperature in Kelvin, subtract the 273 to get the degree Celsius. In theory, at 0 degree Kelvin, matter stops to move. It's so cold that there's no more vibration, rotation, translation whatsoever, and matter moves very little or not at all. And scientists think that at that stage, matter ceases to exist, which is kind of weird when you think about the law of conservation of mass or matter. It kind of boggles your mind. That being said, they've never really achieved it. They've become very close to it, but they never attained the 0 degree Kelvin. What they actually observed when they got really, really close to it is that matters contract so much that basically it doesn't use much space. I guess that's why they pretend or they think that it would cease to exist. It would be so tiny that that amount of matter would be so tiny because it would shrivel so much that it would practically use no space, so basically have no volume and therefore technically cease to exist. But that still has to be proven. Anyways, back to Charles' law. So it says that when we have the volume of a fixed mass of gas is directly proportional to its Kelvin temperature as long as the pressure is kept constant. So we are looking at the volume versus the temperature. And like I said, this ratio always remains constant, which allows us to say that V1 over T1 should be equal to V2 over T2. In other words, if I double my volume, that's because my temperature should have doubled as well. Now, if we look at a few graphs, here we have volume versus temperature in Kelvin, volume versus temperature in degrees Celsius. Now, I told you that the temperature should always be in Kelvin. That's the only way that the rule, the mathematical rule, actually works. If you keep your temperature in Celsius, the law doesn't represent reality. It doesn't work with what we're observing. So your calculations really have to be done in degree Kelvin, otherwise your results will be flawed. They won't be representative of what you would observe in a lab. Now, if you look at the two graphs, you can see there's a slight difference. Here, it doesn't stop at the origin. Here, it does. The reason is the following. At 0 degrees Celsius, right, because we have the temperature here, at 0 degrees Celsius, we know that matter has a volume. If you just think about a piece of ice, an ice cube occupies a certain volume. So the volume is not 0. But if we were to extend that line and see where it ends up, at what temperature my volume becomes 0, and we have an example here, we have 3 different gases. So 3 different lines, right, for the 3 different gases. At 0 degrees Celsius, which is here, they all have a certain volume. But if we extend those lines to see where they end up, at what point there is no volume, and therefore on the y-axis we are at 0. If we take all 3 lines and we extend them, they all end up at the same point, which is 0 degree Kelvin. So that is why this graph here shows a line that ends up at the origin. This is only basically an extension of this one. If this were to be prolonged all the way to volume equal to 0, we'd get maybe here, which represents minus 273 Celsius, or as we know, 0 degree Kelvin. So again, if we look here, your temperatures in Celsius are in black. So if we are to extend all 3 lines representing 3 different gases until the volume is at 0, so until our lines reach the x-axis, they all end up here, which is about, if you look here, it's minus 200, minus 300, it's about minus 275 if we guess, but in reality we know that it's minus 273 Celsius, which is the equivalent of 0 degree Kelvin. And the advantage of using the Kelvin scale is that we'll never have any negative temperatures to deal with. So the calculations are simplified because we only have positive values all the time. so we don't have to deal with negative values. It makes our life simpler, easier. Okay, what's the story now with kinetic theory? Well, if we increase the temperature of the gas, so I have a certain amount of particles, if I increase the temperature but I keep the number of particles constant, they'll start moving faster, right? I'm giving them more energy. Now in this case, we're trying to keep the pressure constant as well as the number of moles. So the only way that, again, I can control the amount of collisions happening in order to not change the pressure is by increasing the volume. So by increasing the volume, I'm giving more space for my particles, limiting the amount of collisions there are, and therefore keeping the pressure stable. So one more time, I have X amount of particles. I don't want to change that. I'm heating up the particles. They're getting more excited, they're moving more. They're colliding more, but I don't want more collisions because I want to keep the pressure stable. So in order to keep the pressure stable and therefore the number of collisions, I increase the volume. So pressure stays the same, number of collisions remain the same, because the particles having greater space to circulate will again take longer to find each other and collide with each other. So I keep my pressure constant, and the only solution is to increase the volume if I increase the temperature. Now, a practice problem. So you only have one this time with Charles' law. It's pretty simple. So let's read it together. Again, you can pause it if necessary. So we have an inflated balloon, inflated in an air-conditioned room at 27 Celsius, has a volume of 4 liters. It is heated to a temperature of 57 degrees Celsius. What is the new volume of this balloon if the pressure remains constant? So let me get some blue. Okay, first of all, I will list my variables. So I have V1 is equal to 4.0 liter. T1 is equal to 27 degrees Celsius or 300 degree Kelvin. V2, I don't know what the value is. I'm looking for that. And T2 is 57 degrees Celsius, which is equivalent to 330 Kelvin. Okay, so now I'm using V1 over T1 is equal to V2 over T2. And let's not forget, I need my temperatures in Kelvin. So I will replace, I have 4.0 liter over 300 Kelvin is equal to V2 over 330 Kelvin. And all you have to do is cross multiply and find the answer. And the answer is 4.4 liter. Now, if I may address the significant figures. Here, in terms of temperature, I'm basically doing 27 plus 273. That 273, let me write it actually to make it clear. Hold on, I need a color. Go here, let's do it in red. So if I write down my temperature, so I have, for example, 27 plus 273. Now this here is a constant. It's not really a measurement. It's a conversion factor, so to speak. So that doesn't count in my sig figs. So I'm going from no decimal to basically no decimal. So I have 300 Kelvin is the equivalent. So as long, since I'm adding, as long as I keep the same amount of decimal, which in this case none, I'm fine. So now when I get to this calculation, I have 2 significant figures, 3 significant figures, 3 significant figures, and so therefore my V2 should have only 2 because this is the smallest amount, and that is why your answer is 4.4 over here with 2 sig figs, not more. Regardless of if you had more decimals here, you'd have to stick to 4.4. So that's it for that. I'll see you for Gay-Lussac's law. Bye!